it is. There is a fundamental limit on just how precisely we can know both the position and momentum of a particle at a given time. Mathematically, this principle can be represented by the following equation, where a change in position and our change in the momentum is going to be greater than or equal to h over 4 pi. Right, so I do not expect that you will memorize this. The important thing to know is that it is impossible for you to know both things 100%. There's a trade-off that happens in information. And this is a fundamental thing in the nature of the universe and the way quantum systems behave. Heisenberg's equation disproved Bohr's model for defined orbits, because if those electrons were in those defined orbits, we would know exactly where they were, right? And if we knew exactly where they were, we'd have no idea of how fast they were going. But we have some idea of how fast they're going, so we don't know exactly where they are. Bohr's theory did not provide a clear description for what was happening inside those atoms. Right? It took Erwin Schrödinger, who derived a complex mathematical formula to incorporate both the wave and particle characteristics of matter to describe those electrons. And so that model, no. So Schrödinger proposed an equation that contains both wave and particle terms. Solving the equation leads to what are called wave functions. The wave function, or more accurately, the square of the wave function, right, that gives us the shape of the electronic orbital, and the square of that wave function gives the probability of finding the electron in a given volume of space. That is the electron density of the atom. So here is Schrödinger. You probably have heard about Schrodinger's cat. I have a nice Schrodinger's cat shirt. He died in 1961. The experiment for Schrodinger's cat is that a cat, along with a flask containing poison, is placed inside a sealed box, shielded against environmentally induced quantum decoherence. If a Geiger counter detects radiation, the flask is shattered, releasing the poison, which kills the cat. Quantum mechanics suggests that after a while, the cat is simultaneously alive and dead in a quantum superposition of coexisting alive and dead states. Yet when we look in the box, we expect that the cat is either alive or dead, not a mixture of alive and dead. So this is really a thought experiment. No cats were killed. Nobody has actually ever done this. It is all about a metaphor explaining the superposition of quantum states. This has practical application when you start talking about quantum computing. The real world, the other real world thing is that you can say that if you look at the thing, you have changed the system. So by making that observation, you have fixed one of the two. So you're talking about collapsing the wave function. In other words, settling it into one definite state or another. Quantum mechanics, or wave mechanics, does not allow us to specify the exact location of the electrons, but we can predict with a high probability of finding an electron within a certain area or a volume. The use of the term atomic orbital instead of orbit describes the electron's position within the atom. So we've got the orbit that came from the Bohr model, and we're going to refine that, and we're going to call it an orbital instead to indicate that it's our Schrödinger type of wave function. Right? So standing waves, right? So they're going to act wave-like. They're not stationary. They do not travel along any length. Only certain orbits have the circumference into which the whole number of wavelengths of standing electron waves will fit. Other waves produce destructive interference of the standing electron waves, so they can't exist. And the mathematical representation of the standing wave is going to be h with that little hat, and that's going to be psi and e psi. So you got, and I do not expect you to know this, right? This psi is going to represent the wave function, which is the function of the coordinates of the electron's position in three-dimensional space, and h is an operator. You guys don't need to know what an operator is. The specific wave function is termed an orbital. The wave function does not provide information about the pathway of the electron, right? So it's not telling you how it's exactly traveling around, right? But if we square that, we get our probability distribution. That indicates the probability of finding an electron near a particular point in space. And to represent these, we're going to use the intensity of a color to indicate the probability value near a given point in space. The more time an electron visits a particular point, the darker negative becomes. This diagram is known as an electron density map. So the probability distribution for the 1s wave function, so we'll get to what 1s means in a second. So if we got an electron, and if we look at the probability distribution of finding this electron, right, so our hydrogen electron, our basic hydrogen, we got a hydrogen, one electron, what is the probability of finding it? Well, if we look at the distance from the nucleus, so the nucleus would be here, right? And as we get further away, right, we're less and less likely to see that electron, right? So as you get closer and closer and closer to the nucleus, right, you're more and more likely to find that electron, which makes sense, right? Your nucleus has a +1 charge. Your electron has a -1 charge, and opposites, they attract. Right? If we zoomed in on this, right, what we would see is that right as we get right to the nucleus, if you remember that Rutherford model with the gold foil, it's mostly empty space. Right at that nucleus, there's not going to be any electron density. So it's actually going to drop off real quick. The other cool thing about this is way down at this end, this guy is going to basically go asymptotic, right? So in other words, it's going to go down to almost, but never ever really quite reach 0. The probability becomes really, really low. And interesting things start to happen when you're somewhere at this intermediate, where you can get things like electron tunneling, where an electron will go from one, it'll be localized around one nucleus and bop on over to another one. And we can actually do that with a scanning tunneling microscope in STM, take advantage of that electron tunneling. That leads to problems, and interesting ones too, with the fundamental limits on Moore's law, which describes how small you can make electronics and how many transistors you can print on a given integrated circuit. So, we are starting to reach the point where that kind of electron tunneling might become an issue with how we build electronics. So that's if we're doing it in one dimension, right? So as you're getting far away, what's the probability? But that exists in not one dimension, but 3 dimensions. So it's a radial probability distribution. It goes in a sphere. It's going to be the total probability of finding an electron in each spherical shell versus distance from the nucleus. The probability of finding an electron at a particular position is greatest near the nucleus, right? So minus charge wants to be near the plus charge. The volume of the spherical shell increases with the distance from the nucleus. The size of the 1s orbital can be stated as the radius of the sphere that includes 90% of the total electron probability. Right? So this is kind of a top-down view from that. So if I'm looking, right, the further away I get from the nucleus in any direction, my probability decreases, right? So, right at the nucleus, I'm not very likely to show up right on it, right? But then it's going to decay as I go away. The cross-section of the hydrogen 1s orbital probability distribution is divided into successive spherical thin shells, just kind of give you some scale there. And then B is this radial distribution plot. So that's what we're going to do to describe some of these electron orbitals. It's going to get a little bit more complicated, right? And we will see that in a second. But what comes out of all of these wave equations from Schrodinger is a series of quantum numbers that express the various properties of the orbital. We've got a principal quantum number, n, which has integral values and is related to the size of the energy orbital. These are the shells that Bohr talked about. We've got an angular momentum quantum number, L, and that's going to have integer values from 0 to n-1. It's related to the shape of the atomic orbitals, and it's sometimes called a subshell. Then you're going to have the magnetic quantum number, m sub L, or sometimes just m, and it's going to have values that go from L to minus L, and it's related to the orientation of the orbital in space relative to the other orbitals in the atom. So when we talked about this guy on our hydrogen, which is in what we call an s orbital, there is no orientation. But some of the orbitals we will see are going to have lobes to them. They're going to look like a peanut rather than a sphere. Right? So you can orient them in X or Y or Z. Now, at first glance, this quantum number stuff, this is new. It may seem intimidating, but if you can use a phone and dial a phone number, you can handle quantum numbers. Or accurately, it's a lot more like an address, right? So you've got my name, a street, a town, a state, a zip code. There's 1, 2, 3, 4, 5 pieces of information. To describe where an electron lives, we've only got an N, an L, an M, and an S. So we only have 4 pieces of information. If you can mail a letter, figuring out where an electron lives on an atom is even easier. Each atomic orbital in an atom is characterized by a unique set of 3 quantum numbers that fall out of that Schrodinger wave equation. N, L, M sub L, and S, M sub S. You can dial any electron on the periodic table by knowing its address, Z, quantum number, N, shell, L, subshell, M sub L, orientation, and M sub S, spin. So with these pieces of information, we're knowing where those electrons are, what shape those orbitals are in, what the probability distribution is. And so even though the math is really a gigantic pain in the butt, and if you like math, maybe it's not my jam, but you can figure out lots of information about an electron fairly easily once you've done all that math. Right, so let's look at the principal quantum numbers, right? N is going to designate the size of the orbital. So when we talked about those hydrogen transitions going from N equals 1 to N equals 6, and then from N equals 6 to N equals 2. These are the N's we're talking about, right? This is the same N. It's going to have values of 1, 2, 3, 4, and so forth. The larger the N value, the greater the average distance from the nucleus. If you want to put in an electron in N equals 2 and move it to N equals 3, that's going to be more energy. The bigger the number, that represents more energy. These correspond to the quantum numbers in Bohr's model, and they're sometimes commonly referred to as shells. Right. The quantum number L defines the 3-dimensional shape of the orbital, and sometimes called the subshell. There are n different shapes of orbitals. L is equal to n minus 1. If n is equal to 1, then L is going to be equal to 0. If n is 2, then you can have shapes of 0 or 1. If n is equal to 3, then L can be 0, 1, or 2, and so on. We commonly in chemistry refer to them by letter or subshell notation, where L is equal to 0, we're going to call that S. And then we'll do L is equal to 1, we'll call that P. L is equal to 2, we'll call that D. L is equal to 3, we'll call that F. And then G, H, I, J, K. The magnetic quantum number describes the orientation of the orbital in space. So if you think about this in terms of X, Y, and Z axes, and it's going to have values from minus L to plus L. So if L is equal to 0, then M sub L can only be 0. If L is equal to 1, then M sub L can be equal to minus 1, 0, or plus 1. If L is equal to 2, we're talking about our D subshells. You can have minus 2, minus 1, 0, 1, or 2. Right? And then if you went to 3, it would be, there'd be more of those. The electron spin quantum numbers describe an electron that occupies a particular orbital, and they can have values of plus 1/2 or minus 1/2. And we call these guys spin up and spin down. So each orbital can hold 2 electrons, and that electron can either be spin up or spin down. You can't have 2 spin ups or 2 spin downs. Right, so if you think about the orbitals as being houses, you can only have one roommate. One roommate stays up all night, and the other one stays up all day. This is just another way to represent this. This is showing our breakdown by N. So if you're talking about N1, you've got L0, M0. You're going to have an orbital notation called 1s. It's got one orbital in a subshell, and it's got one orbital in the shell. If you're looking at n equals 2, you could have L values of 0 or 1, so a 2s or a 2p orbital. And in those subshells, you're going to have 1 subshell in the s and 1, 2, 3 possible orbitals within the p subshell. So you've got 3 orbitals in that subshell for p, 1 orbital for the s subshell, for giving you a total of 4 orbitals in that n equals 2 shell. If you go on to n equals 3, you can have 1, 2, 3 L values. So 3s, 3p, and 3d if we're using our orbital notation. We've got 1 orbital that we could have in s, 1, 2, 3 orbitals we could have in the 3p, 1, 2, 3, 4, 5 orbitals we could have in 3d. So 1, 3, and 5, giving us a total of 9. Right. Here's another way to represent this. We have the name, allowed values, and quantum numbers. So if we take our n, which is our principal or our size, our angular momentum L or shape, our magnetic orientation M sub L. So our allowed values are going to be a positive integer for n. Our angular momentum will have 0 to n minus 1. And our magnetic will have minus L to plus L. Okay. So if we start off with our first one, so n equals 1, we're only going to have 0, 0. We're going to start off with n equals 2. We could have a 0, and we could have a 1. And if we go to our magnetic, well, we only have 1 for that magnetic orientation, and we're going to have 1, 2, 3 orbitals in our p subshell. And if we go to n equals 3, we could have an s, a p, and a d, or a 0, 1, 2, and 3 as our L's. And our 0 is only going to ever have 1. Our p is going to have 3, and our d is going to have 5. Right? Another way to represent this for all of our visual people is here is our orbital, our s orbital, right? So here is L. Right? L is going to be 0, 1, 2, and 3. We are in our s subshells with n is equal to 1. Here n is equal to 2. This is our n equals 2. We've got an s and some p's, 1, 2, 3 p's, minus 1, 0, and plus 1. Each of these boxes can hold 2 electrons. If we go to n equals 3, we've got one S, we've got an S, we've got some 3 p's, and we've got 1, 2, 3, 4, 5 d's. If we go to n equals 4, we've got 1 s orbital, 3 p orbitals, 5 d orbitals, and 1, 2, 3, 4, 5, 6, 7 f subshells, or 7 orbitals available in our f subshell. So what this does, right, this is a representation of what a neighborhood would look like in terms of where are the addresses for each of these electrons, right? So this particular box here is going to have its own unique set of 4 quantum numbers. An electron in this box is going to have its own unique set of 4 quantum numbers, and this box is always there. It doesn't matter whether or not there's an electron in it. Those 4 quantum numbers describe this space. You may or may not have an electron in there, depending on what atom you've got, but they're always going to be existing in potential. So if you've got something like a hydrogen atom, right, with only 1 electron, you have all of this available real estate, just nobody's built it out yet. Right, so your poor little hydrogen electron, right, low energy. Right? If you really excite that from n equals 1 to n equals 4, well, maybe you excited it from n equals 1 to n equals 4, and it ends up in a d subshell. Right? So you could put an electron from here into here. So those spaces are always available. They just may not be occupied. Right? So they might be theoretically available. So let's do an example. For a principal quantum level n equals 5, determine the number of allowed subshells, different values of L, and give the designation of each. For n equals 5, the allowed values of L are going to run from 0 to 4. So n equals 1, right? So you're going to go 0, 1, 2, 3, 4, right? All the way up to 5 minus 1. So that means you've got L is equal to 0, 1, 2, 3, and 4. So that means you can have a 5s, a 5p, a 5d, a 5f, and up to a 5g. Now you might be wondering what this s, p, f, d, and g is coming from and what they look like. Well, the shapes of these atomic orbitals, as we will soon see, here's an easy mnemonic to remember those. The s's are spherical ones. The p's are going to be our peanut-shaped ones. Our d's are going to be double dumbbells, and our f's are going to be fancy floral ones. They're coming from the spectroscopy, which describes some of the lines that you would see in emission spectra. And they could be S for sharp, P for principal, D for diffuse, and F for fundamental, and the rest are all going to be named in alphabetical order. The areas